Welcome back. How's everyone doing? Good to hear. Not quite as many as there was on Monday, but that's to be expected, so you're here. Just a couple things. I am working on the exams. I don't have them ready, no. But over the weekend, I will. I'll enter them into, what I do is as I grade them and enter them in, they don't post as I enter, so I'll get everything done first, and then everybody will get posted at the same time. So I'll do that over the weekend. So by Monday, you'll have it, probably earlier than that, though, maybe Sunday night. This is a good time to think about what's been working for you in your studies and everything, and maybe what didn't go so well, and try to work towards doing more of the stuff that's been helpful, and get yourself on track. I've looked over a few of them, and it's probably going to be like there'll be some that did very well and some that didn't do as well as you would have liked, and maybe where you're at. Here's the thing I do with you, though, to keep you engaged and keep you going. We have a final exam that is comprehensive. So if you didn't do as well as you would like on this exam, I will look at how you did on the final, and that's the final assessment. If you do well, if you learn this stuff still, and it shows up on the final, it's going to cover everything, right? But it'll cover this stuff. I don't say exactly what I'll do, but I will make sure that if you can show me that you've learned the stuff, your grade will reflect that as well. Okay, so don't think, whatever the score is now, that's not the final thing. I do make what I call a holistic assessment, which is I look at everything you've done. I have opened up the homeworks thank you. I don't know what I do with each class, but they're at least open till Sunday. So you can go back in there and work on them, not just to get the points, but it gets you points, but to learn the material. If you get locked out of some of the questions because you've maybe tried the 5 times or something, do it on paper. And again, we'll take a look. If it makes a difference, as long as you've learned it, we'll get it in there. Okay? So I'll work with you. The main thing is to learn the content. Any questions? All right. So, where are we? So what I've done in my Canvas is I've put learning materials for test 1. I've closed them out. I'm not going to worry about them for now. Yes.
I was watching one of your lecture videos. You said if you get 80% on the assignment, then it's basically 100. Does that still apply?
Yeah, I think I do that. Do I do that? Did I do that with you guys? Well, if you do the homework up to 80%, I give you 100%. Can't believe I did. Usually, yeah. So if I did it before, why not do it? I usually do it in my other ones. Anyway, it's a manual adjustment, though, so when I do the updates, I have to. I may have just done the other one. Yeah. So you get to 80%. I think I did that because here's the thing: is WebAssign sometimes locks you out of something and you actually know it. So I might have said 90, but if I said 80 in the past, we'll do 80. I'm okay with either one. So as long as you're doing the majority of the stuff and getting those things done, again, there's a few that you might not get credit for because of WebAssign, but you understood it. So that's why I go with the 80 and give you all the points. The thing is homework points aren't going to do them alone. But learning from them will help you on those tests. Those tests all math classes were required to be 70% or more of your grade has to come out of a test. There's a few classes you might get 65, but that's what the department requires us to do. So we'll do that. So yeah, but keep me honest if I haven't done that already. This weekend I'm traveling to Oregon, the Oregon coast. It's a family thing. Actually, we've got a little bit of time, but intergenerational. So you got families, right? And I'm sure in your families you've got grandma who thinks one thing, mom and dad who think another thing. I've got a 102-year-old grandmother, still alive. My mom passed away about a year and a half ago, 80 years old. She didn't make it as far. She asked us to spread her ashes at the Oregon coast. Grandma doesn't believe in spreading ashes. You've got to keep the body together. That's just her beliefs. But so I was flying into Seattle to visit her, but I'm going to have my brother pick me up, and I'll wait till after we do the ashes. So sometimes you just got to do what you got. I promised my mom I'd do it, right? So I got to do it for my mom, but I don't want to go talk to grandma and have to deal with it beforehand. So, anyway, that's problem solving, right? That's what we're trying to teach you, these things, is kind of figure these out. So anyway, but while I'm in my brother's car driving down, there's about 6 hours in the car. I'll be grading exams, not much else to do. My brother likes to talk about sports and stuff. I'm not so much into sports, but I'll look like I'm listening, but I'll be grading, so I'll listen a little bit too. But, so here we are. Get back to the topic. I put these pacing calendars in, and so your Monday, Wednesday courses first. We're going to take a look at something called the chain rule. This, again, it's not really anything new as far as taking a derivative. It's really the same process, but it's like the product rule and the quotient rule. There's kind of going to be a formula that after we take the various derivatives, we put it back together. And it's a chain rule because a chain is connected to each other, and so we're doing stuff with a composition of function, where one function is the input to another function. So that's the idea of the chain. Okay. For the most part, it's going to be the same thing. Whatever the exponent is, it comes down in front and multiplies, and you subtract one from the exponent. Okay, so that's the same thing we've been doing. So as far as taking the derivative, it's nothing new, but we're going to have a little process, and we'll walk through it. This is where we start to get some new stuff, is when we look at logarithmics and exponentials. Those operate differently. So we'll actually get some new skills. Implicit differentiation, so we start doing some applications. We move through it. We've got a day for review. 12.6 is in the homework. I'm going to count that as extra credit. It's not on the exams. So I thought, to get the timing, if it's not on the exam, let's not cover it. I will have a recorded session, so if you want to do it, it'll be there, and it'll count as extra credit. If you don't want to do it, you don't have to do it, and there's no points lost. But if you're behind, I know you'll do it because you want the points. And if you're doing well, you'll do it because you do everything. It's just human nature. So it's a good thing to do. Okay, so let's go ahead. I'm going to jump into 11.4 now, the chain rule. And what we're going to be able to do now is something like, let's go with blue, a function like this. Now this is a 0.5, so something to the 0.5 power could also be written as square root, right? So we know how to take the derivative of a square root function, right? We put it to the 1/2 power and bring it down. We could do this as x to the 0.5. So when we take its derivative, we're going to get 0.5x to the minus 0.5. So we've done this already. But we've never talked about, well, what if I don't just have x, and what if I got other stuff in there? So that's what we're going to do today. We're going to learn how to take the derivative where we sort of have an outside function, x, the square root of x, but we've also got a function inside there, more than just x. Okay? And again, the techniques are really not going to be anything different. It's just we'll end up taking derivative of the inside, derivative of the outside, multiply them together, and that's the magic. So it's nothing ultimately new, but you have to recognize that that's what we're doing. Okay? So we look at this function, as a composition, that it's actually two functions in there. Okay, so let's see what my next slide. I changed these up a little bit, so we'll do this. So thinking about how we would calculate that, not necessarily take the derivative, but what we would do is we would plug the x sort of into the inside part first, right? And then we would take its square root, right? If I gave you, said, let's find, I told you x equals, let's see what would be a good number. X equals 5. What would we do? Well, we would take 3 times 5 plus 1. That gives us 15 plus 1 is 16. And then we would take its square root, take it to the 1/2 power, right? And we would find that our final answer would be 4. So this is, we've done this before. You plug it in, do the inside stuff, and get it. That's kind of what we're going to be doing, the process we're going to be following with derivatives now. We're going to take that inside stuff, take its derivative, and then we're going to look at what's the outside, just look at it as sort of a new function, take its derivative, and then we'll see that by multiplying them together, we actually get what we're supposed to get. So just like we would follow through if I asked you to get h of 5, you plug in the 5 inside, and then you do the outside part. Okay, so here's our example. And they use, here's another thing, when I was going through this, I just couldn't believe it. But in math, they oftentimes do things. So they usually use this, they call this sort of u substitution. So they use u, but when you take a function f and then u, I don't think it's very polite to tell people fu. So I changed it to fi. And I stands for inner, and it's more descriptive, right? So there's an inner function, and then there's the outer function. That's what we're going to do. See if it makes sense. Okay, so if you see a few random u's in here, it means I missed something. Okay, so we've got this combined function that really is f of I of x, right? What's the inside function? Well, the inside function is just 3x plus 1. What's the outside function? Well, let's think of it as something to the 0.5 power. You could do x to the 0.5, but this is a composition, right? So what we're going to do, I might be getting a little bit ahead of me, but when we go to take its derivative, we take the derivative of I and then multiply it times the derivative of f with the I function inside it. Okay, you're going to see that. So because right now it has it inside. Okay, so we're going to do this a couple different ways, but what's the derivative of the I function if I were to take this derivative? What's the derivative of 3x? 3. What's the derivative of 1? 0. So the derivative of the inside is just 3. What would be the derivative of the outside function? That's x to the 0.5. Again, something we just did. The 0.5 comes down, 0.5x. We subtract 1 from it, so 0.5 minus 1 is minus 0.5. And we're going to see this is really what we're getting. Think of this as I of x. We're going to back substitute. So our final is going to be the derivative of I times this derivative. But we're going to place the x with what was in there. Okay. And then we could take 3 times 0.5. Those are together out there, right? So it's like 1.5. Let me, I've got a couple other ones where we'll step through it a little bit. But the chain rule is take the derivative of the inside, take the derivative of the outside, and usually we'll use some other letter here and then we'll replace it. So this should actually be sort of like I, and in the following slides we'll do that. So derivative of the inside function, derivative of the outside function, and then put them together. Okay. So again, this walks us through again. If we were taking, if we did the composition, we want to plug in 1. Yeah, there's still a u left over. So that should be I of 1. You plugged it in, you'd get 4, because 3 times 1 is 3, plus 1 is 4. And then you put it into the outside function, f of 4, the square root of 4 is 2. Okay, so that's how we do it. So we always compute from the inside out. Given x, first compute I of x, and then compute that. So we're going to kind of do that with the derivative. And the chain rule says that we've got these two functions, the outer function and the inner function. So when we get its derivative, we're going to take the derivative of the inner function, and then we're going to multiply it by the derivative of the outer function with the inner function in it. Okay, so on the chain rule, you'll know you did it right because you already see that inner function kind of stays there, nothing happens to it. And then there's a derivative of the inside part, and then there's a derivative of the outside part. A lot of parts, right? Is it making sense yet? Not yet. That one? Oh, this one. Okay. So this is what we're going to do. Okay. So we're going to take the derivative of a composition of functions, which is some outer function with an inner part, and I replace all this notation with just the word inner to make it, because it could be complicated in there. So this first part here, and they do this in the book, and they kind of mix the notation, right? They've got the prime, which means a derivative here. Do this. So that's the derivative of the outside, and they use this d dx, so the derivative of the inside. So I'm trying to do it in sort of the order they say is, let's do the inside part first and then the outside. You could, since we're multiplying them, right, you could do it in either order. So if one feels more natural to you, go ahead and do it. I'm going to do this because typically what students will do is they'll do the outside, but they'll forget about the inside. So let's just do the inside part first, and we'll see how that works. So in words, we're going to take the derivative of the inner part, inner function. We're going to multiply times it by the derivative of the outer function with the inner function in there. Okay, so, and we're going to, here's another way, this is the way the book wrote it. So we'll take the derivative of the outside function, and this would be the derivative of the inside function. Again, they're using u. But that was an image. I couldn't really easily change it, so we'll bring it in. Okay, so here we go. One example, if we're doing some inner function squared, what we want to think of is as we take this derivative, right, what is something squared? It would be the 2 comes down, that's this part here. We subtract 1 from the exponent, so this really was 2 minus 1, which becomes 1. And then we take, here we're going to take the derivative of the inner. Of course, right now we can't, right? But this is just equivalent if we had x squared, and we take its derivative, right? We're going to get just 2x. And then what we would do is the derivative of x. What's the derivative of x? It's 1. So actually, in a way, we've always been doing the chain rule, but we just haven't called it that because 1 times 2 is 2. So let's take it one more step, and I think it'll become clearer. They do the same thing with the cubed function. So again, this is just an example. So u cubed, the 3 comes down, subtract 1 from the exponent, so that's 3u squared. But whatever's that u function, whatever that inner function is, you've also got to take its derivative. So just remember that that's going to be the chain rule. And they show an example that they could do it with the product rule, but I think that was more complicated. So let's look at some examples. I'll put this here. This is probably going to make more sense if you look back at it later. But it's just saying that, this is really, the chain rule is nothing new. We've been doing it. X squared was 2x times the derivative of x, right, which is 1. But this time, we're going to have the inner function is going to be more complicated, more than just x, more than just u. So what we're adding in is, remember, to take the derivative of the inner part. Okay? So that's what all of these are saying. And again, when you go back to it, it might be a nice little thing to take a look at, but let's do a few together. And I'm going to do these maybe in a couple different ways, and hopefully something clicks on you. Okay, so to take this, what is the inner part? What would you say would be the inside function? Good. 2x squared plus x. And at this place, you can kind of note, you see the parentheses. It's the stuff in the parentheses. What is sort of the outer function? It's something to the third power. It's the inner to the third power. Maybe I should write it that way, huh? Just to show. So let's take this. This is our sort of outer function, right? Let's go ahead and take its derivative. We've got something to the third power. What's its derivative? 3 times the inner stuff. And then we subtract 1 from the exponent, right? 3 minus 1 is 2. What's the... Yes? It's the outer derivative. So we're going to see, and we'll replace this word inner with the function. So okay. So this up here is the inner. So what would be the derivative of the inner? Let me change color. Okay, so the derivative d dx of the inner and again, we've got this inner part. Just let's take its derivative. 2 times 2 for x to the first power, right? And then derivative of x is 1. So that's the derivative of the inside, and this thing, the derivative of the whole thing, is going to be the derivative of the inner times the derivative of the outside So what was the derivative of the inner? Well, that was 4x plus 1. This is 3, and then we can sort of back substitute. What was the inner? It was 2x squared plus x, and this is now squared. So let's see. Sometimes it's easier to do. So here's the inner part. This is the derivative of the inner part. And this is sort of the outside part's derivative, right? It was something to the third power. It's now going to be 3 times the inner part. We can't distribute this 3, can we? Because this is, we'd have to square this, but we're fine to leave it just like it is. You don't have to, quote, simplify it. Because it, yes?
Would 3 multiplied as 3 by the first inner instead of on the outside?
You could just, yeah, because this is really this times this times this. So you could take this 3 and distribute it through. So it would be okay to do this as 12x plus 3. We'd have a parentheses now because we distributed that, times this. But usually they don't require you to do this, and I prefer not to because we've lost what happened. Notice if we have this, we can kind of see, I can look at this and I can see the outside derivative and the inside derivative. If I go to simplifying, I lose what happened. I'm not really sure that that's the derivative anymore. I don't see, oh, I had something to the third, but here I see the third, I know where this 3 came from, right? It came down from the exponent. I want to leave it there so I know I did it. I've got the second power here, and I can see that this first part is the derivative of the inside part. I can see all those parts. And the reason is because the second half of the class where we're going to integrate, we'll start with this and we'll ask you to get back. And so if you leave it this way, you'll get used to seeing it this way. And so when you're asked to go backwards, it'll be easier. But you're right, you could do this, but it's really not helpful because it puts it in a different form, but we lose the information of what went on. We're okay with that? Question?
So your class that's reading
Oh yeah. In fact, I would prefer it. I was looking over the exam. Some of you did some simplification, but I don't even look at the simplification. If you did multiply out, I look at that. I said that's what I'm going to concentrate on because I could get lost in there. And anyway, yeah. Again, this is what we're looking for. And I believe WebAssign will do the same. If they're not, we'll write them a nasty letter and say that they should be because this is the better way to do it. Okay, so then there's a couple slides where this is the textbook walking you through, so I left these in here, but I don't, if I just talk through these, it's kind of boring for me, probably boring for you, but it kind of will walk you through that you can just kind of think of it, and sometimes you just say, okay, cover this up, this is something to the third power, so that's 3 something to the third power, and now it's squared because I subtracted 1. So I took the derivative of the outside first, is usually how I would do it. And then I just have to remember this inside stuff, right? Because it's always going to be there. I need to take its derivative. And so I do it sort of up here. 2 times 2 is 4. X to the 1 power. Derivative of x is just 1. So that's how I do it. I take the derivative of the out, because for me it's easier to see the outside stuff. And if it's in a book, you could cover it up with your thumb and you can see, okay, the 3 comes down, it's down to the second power, it's all that stuff there. And then just remember, take that inner stuff and make sure you take its derivative. So whichever way you want to do it.
So it doesn't matter how you, what order you put it.
No, it doesn't, because it's all multiplication anyway.
And that's it.
That's it, yeah. So notice it's not really anything new, but you just got to remember, we've got this, be able to see the outside function and the inside function, and you're good. That's why in algebra class, we did so much with composition of functions. It's not because algebra really needs it that much, it's because we need it here for the chain rule. It was preparing you for this. That's why we do it. Okay? And they do it with substitution of letters. For me, you start, okay, call this u to the third, but it's just easier, I could see. Cover it up with your hand, bring the 3 down, and then leave this thing in here, and then take its derivative. That's really the steps. So let's see if we can, I've got a couple other examples in here. So this walks you through another way, using this u thing, and okay, we got that, and what is u? It's this, and then take its derivative. So those are there. Again, these were the same problems, so multiple ways of kind of going through. Take a look, and maybe one makes more sense than the other. They're all ending up with the same thing. Here's our 3 to this is the something, the inner part to the second power. This is the derivative of the inside part. Okay. So and then they give a verbal where they kind of talk you through it. And again, they arrive at the same thing. So I just left these slides in. If they're helpful, take a look. But let's take a look at this one and see if we can't do that the same way. So what's the inside part? the stuff inside the inner parentheses, right? And so when you take this derivative, just see this as something to the 100 power. Something to the 100 power, how do we take its derivative? The 100 comes down, the exponent comes down, multiplies by that stuff, something, which is x cubed plus x. And then what do we do with the exponent? We subtract 1. That's half of what we've got. Now there's one more step. What do we need to do? Derivative of the inside, the stuff in the parentheses. And notice, if you do it this way, it sort of just follows. I've got this stuff, everything's ready. So now I just need to take the derivative of the inside stuff. I'll put a parentheses. What's the derivative of x to the third? 3x squared. And then the derivative of x is 1. Okay, so that's, and for me, going to the u substitution, that's probably why I had to take calc twice. I didn't understand what they were doing so much. Yes.
Can you do a practice problem with a fraction?
Yeah. Fractional exponent, you mean, or?
The homework is f of x equals 1 over 7x minus 3.
Oh, sure. Actually, I think I've got one. Let me go through these and hold on to that. But so questions on this one. We're done here, aren't we? And when you look at the answer, do you see an outside function? Right? Just kind of cover this up. Yeah, the 100 came down and 99, and then I can see here, this is the derivative of that inside stuff. And with the chain rule, you'll always see that. You'll see that function doesn't go away because the derivative on the outside's happening, but then you've got to get that derivative of the inside. And again, this will talk you through it. I leave it in here if you want to read it later. Symbols, can they go through it? So here we go with a square root function. So similar to the one we started with. So let's think about this one. Again, to take its derivative, let's actually rewrite it, right? It's really 3x plus 1 to the 1/2 power or the 0.5 power. Which do you prefer? You want the 1/2 or do you want 0.5? Any preference? 0.5? I like 0.5 too. Good. But maybe if you've been practicing, so that's a square root function. So now when so I haven't taken the derivative yet. I'm just rewriting it so that it's got an exponent. Now when I go to take its derivative, the 1/2 comes down, 0.5. 3x plus 1. Notice I'm not taking a derivative at this point. I'm just copying because it's the function, right? And then what I do to this exponent, subtract 1 from it. That's the derivative part. 0.5 minus 1 is negative 0.5. So I've now got the derivative of the outside part. What's left to do? The derivative of the inside part. What's the derivative of 3x? What's the derivative of 1? 0. So it's just that. That's it. And again, you could simplify this. We could take 3 times 0.5 and get 1.5. But my way of thinking is I would prefer to keep this because it's got all the evidence. I know where that 3 came from. It's a derivative of the inside stuff. If I combine too much stuff, I don't see that anymore, right? I'm feeling good about this. I can see that this was a derivative taken from the chain rule. And I can go backwards when I need to. Okay. But again, you could take 3 times 0.5, and I don't know, some professors might prefer it. I don't. I just don't. Math is about the structures and being able to recognize what's going on. Simplification doesn't always make things simple, does it? We're okay with that? So again, just see the outside, just sort of cover up the function. Take it like we've been doing. We just have this extra step that the inside is more than just x. So we take its derivative and we're good. And again, there's some verbiage here that will walk you through it. And you'll see they got the same thing we did. And I think they just leave it like that. Nope, they simplified. Again, I don't like this because where'd that 1.5 come from? If I look here, I know where that 3 came from. It's a derivative of the inside. So, see, I think we have an application. I did put one extra and one in here. Let me do that one first, and I'll come back to this as a method. So we'll come back. I think we'll talk about that. No, I didn't put one with a fraction. Let me do this one, and then we'll maybe do the fraction one. So this one's a little, and again, I took this from the homework just so you could see. Do we need to use a chain rule on all of this? No, because there's this addition, it's really two things. The 8x, it's just 8x, right? We could take that derivative. So, and this is a profit function, so they want the marginal profit in this question. So I take the derivative of 8x is just 8. Notice I don't have to worry about a chain rule because x is just x. But if I take the derivative of this square root, the inside's kind of complicated, right? So again, what I'm going to do is maybe think of it as 4x plus 10. This part I'm going to do the chain rule. So when I take its derivative, the 0.5 comes down. I subtract 1 from the exponent. So again, I bring it down, subtract 1 from the exponent, so that's going to give me a minus 0.5. And then what's the last step? I take the derivative of the inside stuff, which is derivative of 4x is 4, derivative of 10 is 0. So it's not that much, but it's something, right? We got this extra thing coming off. And so my derivative, my marginal profit is going to be plus 0.5 4x plus 10 to the negative 0.5 power times 4. And notice I'm going to leave it that way because, again, it tells me I can look at that and I can say, yeah, I used the chain rule properly on this thing. I can see that 4. I see where it came from. It's the derivative of the inside part. And if they need me to calculate something, I could still plug in x and still do all the calculations, right? Put in my calculator if I need to. So it's just as useful as if I were to simplify and take 0.5 times 4 and get 2. Maybe some people like that, but again, I like to have all the evidence that I did everything. So got lots of time. How we doing? Okay, you had a question about doing with a fraction. This is from the homework. Which question number is it?
3.
Number 3. So let's go ahead and do. What was the function they give us?
F of x equals 1 over 7x minus 3.
That looks hard, doesn't it? Do we need to use the quotient rule on that one? Good. No, because there's no function in the top. What should we do with this thing? Make it look a little easier. Because fractions are scary, right? What could we do to make it not a fraction? Excellent. Take the whole thing, think of it, and sometimes, again, they didn't put parentheses, right? But we could think this is a group of things, so we could write this as 7x minus 3 raised to the minus 1 power, right? And so now it's just, we got that exponent, bring the negative 1 down, subtract 1 from it, take the derivative of the inside stuff. It's not so scary now. But when it was a fraction, it's like, what do I do? Probably thinking the quotient rule or something, right? But we don't need that. So when we go to take this derivative, the derivative of this function, the negative 1's going to come down, so I'm going to put this negative 1. The inside stuff stays there. I subtract 1 from this exponent, so I'm going to get negative 2. And then I take the derivative of the inside stuff, which just happens to be what? 7. Just 7. That's it. And I've used the chain rule, and I've got the appropriate function. So that's kind of the part of this homework, is to start to see things as an inner and an outer function. Yes?
If we were to like not simplify it, right? Would it count it as correct?
It should. I'll count, I can always go back and manually do it, but it should, because it's the way it checks it out. If it's not, you could say, okay, I'll put this as -7, But it should. I think it should.
Could we classify the inner and outer as f of x and g of x?
You could, exactly. And that's sort of where they started. They did f of x and u of x, and that's why I broke away from that. But then they thought it was too complicated, so they went with just f and u.
Okay, how would this work if like 7x minus 3x on the bottom is a square?
You would do the same thing when you moved it up, but this would be -2.
Okay.
And then you just get -2 coming down here. This would now be -3. So it's, and if this was more complicated inside, this derivative over here would be more complicated. But you would still see this, again, you're always going to see this sort of unchanged. That's how you know you use the chain rule. You see the function, the inner part, repeated.
What would be, so when you take the derivative of 4x plus n, what is that step?
That's
To get that full-
this.
Yeah, yeah.
That is the derivative of the inner. So you're seeing, so again, I sort of just cover it up, take the derivative of the outside, so the exponent comes down, subtract 1, and I'm just rewriting this. I'm just saying it's one big thing. And then when I get over here, okay, now identify where the inside is, take its derivative. And I find that works better for me than on my scratch paper doing it separately and then trying to put it together. Okay. Let's see this thing. Okay. I guess we could work backwards. Take the derivative where u is cubed, but u is not u as a function itself. Again, what it really is think of it as, right, that's what it's a composition of functions. And so when you take its derivative, what you're doing is you're taking the derivative of the outside part. So again, just kind of cover up those parentheses. It's just think of it as something to the third power. And so the 3 is going to come down in front, and we're going to subtract 1 from it. So we're going to have 3 times this stuff to the second power. What's in there? Same stuff, 4x plus 1. And then the last step, take the derivative of what's inside here. What's the derivative of 4x? 4. What's the derivative of 1? 0. And then again, you could do 3 times 4, or you could leave it like this. And again, to me, especially at the beginning, leaving it like that is purposefully seeing, you see that 4 comes from the derivative of the inside stuff. You see that 3 came from the exponent. And as soon as you multiply and put 12, you say, where did that 12 come from? I don't know. So there's a benefit for doing that. Now, if the homework requires it, okay, go ahead. I can't say 100% for sure, but it should take that. I would do this on my paper. If the first time it doesn't accept it, I would multiply it, and if it takes it afterwards, let me know. And I can't change what it's going to accept, but at the same time, I don't want that holding you back. But on my paper, I would just leave it like that so that I can see the process. And I can come back tomorrow and I'll see, because if I put 12, if I take this 4 times 3 and put 12, tomorrow I'll look at it, I'll be honest, I'll probably forget where that 12 came from. And I won't be able to see it. But if I leave it like this, it will emphasize the derivative for me. Okay? How are we doing? You want to see a long, boring one? I think I'll leave that as an example. If you want to look through it, we don't give you one like this in the homework. There's a lot of just practicing, and I think that's what you need to do. When we get to the logarithms and the exponentials, that's where we really use the chain rule a lot, and we'll start getting some examples like this, applications. But what I'd like you to do is get some practice with just doing the chain rule and seeing how it's really something that's simple, but it's also, I know it's like everything's floating around, and you've got the product rule, you've got this chain, you've got the quotient rule, and now we got this chain rule. Chain rule in some sense can actually be a little bit easier because, again, as long as you can see the inside and outside stuff, take the outside derivative, you'll have that inside stuff there, take its derivative, just write it next door, and you're done. Okay. Again, sometimes, like we did on this this fraction, you might need to rewrite it. This last one here, number 3, rewrite it as as some exponent, but if you got a square root, write it as something to the 1/2 power, but just take that outside, rewrite it over, take that inside, multiply, and you're done.
So it's 7x minus 3 squared.
So it would be to the -3. Because if it was squared, this would be -2. You subtract 1, you'll get -3. Yeah, if it was to the 57th power, no problem. It's a -57, subtract 1, it's now -58. So, as long as we can write it as something to a power, and that's really all we can do at this point. That's the only type of derivative we know is something to a power. We bring the power down, subtract 1. That's all it is. And then just remember that there's this inside part. We've got to take its derivative, and that's going to be the same thing happening. So we get this practice. And that's what I mean is as we go forward, you're going to get practice with this. Some of the stuff that you were doing before that wasn't completely clear is going to become clearer for you. And that's what I mean. You're going to do better on that final than you maybe did on this first test if you struggled a bit. And that's what I want to catch, is I want to catch you doing better, your improvement. Yes?
So how is like 1 over 7x minus 3? Like, let's just say it was like 2 or 3 over 7x minus 3. How do you do that?
2 or 3?
Yeah, just pick it up.
Sure, let's do this. Keep that. Give myself something. So let's make something up. So like 2 or 3, 3 over. Let's do something different. Let's go with 5 x to the 5th minus 27 x to the 3rd raised to the 15th power. So what would be our first step with something like this? Now, first of all, looking at this, why do I know I don't need the quotient rule? Because I don't have what in the top? I don't have an x. Now, had I had 3x plus 1, then that's a whole different story. And you'll see that they won't throw that at you this time, but down the road, you might have to do the chain, you might have to do the quotient rule with the chain rule in it. But right now, we're just going to go with, we're trying to keep it simple. This is the chain rule stuff. So that's, what could I do? The 3 is in the numerator, it stays up there. The elevator rule says bring this up, 5x to the 5th minus 27x to the 3rd raised to the 15th power, negative 15th power, sorry. You can't just make it, yeah, so that's right, that's all we have to do. Now that 3 is just sitting out there, it's a constant multiplier thing, right? When we go to take this derivative, what do we do with the negative 15? We'll subtract 1 from it, but first we bring it down. Now if you want, you could multiply it by the 3. You know, it's up to you. But negative 15 times 3, you could put negative 45. Maybe you would see, okay, there was a 3 there and I multiplied by it. Or you could negative 15 times 3. And then I've got all this inside stuff, nothing happens to it because it's sort of protected. It's got like a bubble around it. And then I'm going to subtract 1 from this exponent, right? Negative 15 minus 1, negative 16. And then I just have one more step, and I'll do it in red. I need to take the derivative of this inside part. So I put those parentheses because I'm going to multiply by it. What's the derivative of 5x to the 5th? 5 times 5? 25x to the 4th. And then 3 to, oh, why'd I change such a, I don't know what 3 times 27 is. Anyone can help me? It's a big number. It shouldn't, 60, 70, 80, 81? Oh, it's 81. I should have known that. 81x to the 2nd, right? Subtract 1. So it's just bring the exponent down, multiply, and subtract 1 on the inside, and then that's the derivative. Okay. And again, sometimes you might want to, you know, maybe go ahead and put negative 45 here. That's okay. You know, whatever feels best to you. But it's okay. It's also okay with me on the test. I would count this full. Go ahead. Yeah, 15 times 3. I see that this was the exponent and this was already there. I see this is 1 less than the exponent. Okay, I can see that happen. And then I see that this is the derivative of this. If I can see that, I'm happy. If you can see it, so write it in a way that works for you, so that when you look at it, you can see it. And I said the whole test of it is look back at and do this. Do the work, but come back 1 or 2 days later after you've moved on to something else, or maybe next week, and see if your notes make sense. See if you could take a look and say, yeah, I remember that. Kind of do this continuous review as you go through the semester. Keep looking back, and what you'll do is because you'll train yourself, you say, oh, I don't know what I did there, I've got to go this. You'll train yourself of what you need to write down so that when you look at it later, you'll know what you did. That's the work you need. You don't need to prove anything to me. You need it so that when you look at it, you know what happened. Okay? Ready for a good weekend? Awesome. I think it worked well. That's probably the best chain rule. Well, you'll let me know if it worked. Okay, good. That was the goal. Because it's usually not. It's because they use all this, so I try to change the notation and
So what you say was the extra